The colonist turns their head to look at a colleague across the room. It takes about a third of a second. In that third of a second, the inner ear, the small fluid-filled organ that tells the brain which way is down, receives two conflicting signals simultaneously. The rotation of the centrifuge is pushing outward through the floor. The head movement has just changed the axis of that rotation relative to the inner ear's orientation. The brain, which evolved to process one gravitational signal at a time, tries to reconcile both and cannot. The room doesn't tilt in the way a car skid tilts. It tilts in a way that has no Earth reference, a smooth, nauseating swing that doesn't stop when the head stops moving, because the centrifuge is still rotating and the inner ear is still reading the result of the turn. A centrifuge on the surface of Mars is not a gravity generator. It is a machine that trades one biological threat for three mechanical ones and charges you full planetary gravity for the service. The engineers who designed it ran the numbers correctly. The math for generating one Earth gravity through rotation is not complicated. Spin a structure fast enough at a given radius, and the outward force felt by anything inside equals the weight that same object would have on Earth. On paper, the problem is solved. The biology is the part the paper didn't have a column for. Building the centrifuge small keeps the cost manageable and the structure achievable with the materials and energy a Mars mission can realistically launch. A small structure means a short radius, the distance between the center of rotation and the floor where the colonists stand. A short radius means the floor is spinning fast enough to generate 1g, but the ceiling, 2 meters above, is spinning at a slightly different speed because it sits at a different distance from the center. The head of a person standing inside is already experiencing less centrifugal force than their feet. The difference, in a structure with a radius of 10 meters, is roughly 15 to 20%. 15 to 20% sounds like a rounding error. For the cardiovascular system, it reads as a continuous, unresolvable pressure gradient. The heart is pushing blood upward against a force that is weaker at the head than at the feet, which is the opposite of what Earth's gravity requires, and the opposite of every fluid regulation system in the human body was calibrated for. The body is not in Earth gravity. It is in a gravity field that changes with height, and the change is large enough that the cardiovascular system cannot settle into a steady state, because the state keeps shifting with every movement. The scale question arrives immediately. Make the radius longer, 100 meters, 200 meters, and the gravity gradient across a person's height shrinks to a fraction of a percent. The physics works. The floor and the ceiling are now close enough to the same distance from the center that the body reads them as identical. A structure with a radius of 200 meters spinning to generate 1g is larger than most city blocks on Earth. On Mars, it must be fabricated from materials transported from Earth or processed from Martian regolith, rock and dust that contains no structural steel, no aluminum alloy, and no preformed load-bearing components of any kind. It must be assembled by a crew that arrived with finite construction capacity and finite energy. It must spin continuously for the duration of the colony's existence, supported on bearings that carry not just the rotational load of the structure itself, but the full downward force of Mars's gravity pressing the entire spinning assembly into its mounting points. That last sentence is the one the scale diagrams leave out. In orbit, a rotating structure carries its own weight in free fall. The bearings that hold the rotation assembly experience only the forces generated by the spin itself, and those forces are manageable because the structure is essentially weightless. The moment the same structure sits on a planetary surface, Mars's gravity is pulling the entire spinning mass downward continuously, and every kilogram of that structure is pressing against the bearings at the mounting points with its full weight, plus the dynamic loads of rotation. A 200-meter centrifuge, massing tens of thousands of tons, spinning on a planetary surface, is loading its central bearings with forces that compress and shear the bearing surfaces on every single rotation. Not occasionally, continuously. Every rotation, for every hour of every day, for the years the colony operates. Bearings wear. On Earth, Industrial bearings in high-load continuous rotation applications, the kind used in wind turbines and industrial mills, require inspection every few thousand hours and replacement every few years under controlled conditions, with a maintenance crew, spare components, and a supply chain that can deliver replacement parts. On Mars, the supply chain is a 9-month transit window. The spare components are whatever was launched with the mission in a manifest that had to justify every kilogram against oxygen, water, food, and medical equipment. A bearing failure in the centrifuge's central mount does not produce a gentle slowdown. It produces a structural event, a sudden load redistribution in a spinning structure of enormous mass under full planetary gravity with the colonists inside. The engineering answer is redundancy, multiple independent bearing assemblies, each capable of supporting the full load if the others fail, inspected on rotation so that one is always being serviced while the others run. The redundancy answer is correct as far as it goes. It extends the time between catastrophic failure and scheduled maintenance. It does not change the wear rate on each individual bearing because the load driving that wear, Mars's gravity pressing the spinning mass into the mount, is constant and cannot be reduced by adding more bearings. More bearings means more inspections, more spare components in the manifest, more maintenance hours pulled from the crew's schedule. The machine that was supposed to free the colonists from the biological cost of Mars's gravity becomes the single highest maintenance system on the base, consuming crew time and spare parts at a rate that competes directly with every other system required to keep the colony alive. This is the bind that no radius resolves. Build small, the gravity gradient destabilizes cardiovascular function continuously, and the Coriolis effect, the nauseating rotation artifact, is severe enough at the spin rates required for a short radius that normal movement becomes a daily neurological assault. Build large, the structure becomes mechanically catastrophic to maintain under planetary gravity, with bearing loads that no reasonable maintenance budget can sustain for the multi-decade timescale a permanent colony requires. The colonists living in the small centrifuge are being slowly damaged by the machine designed to protect them. The colonists in the large centrifuge are one bearing failure away from an acute structural event with no recovery option. Neither version of the machine is stable. They fail in different directions, on different timescales, through different mechanisms, and the choice between them is made before the colony launches, encoded in the structure that arrives on Mars and cannot be changed once the colony is operational. The Coriolis effect deserves its own careful description because it is the problem that scale partially solves and never fully solves. When something moves inside a rotating environment, a person turning their head, reaching across a table, walking from one side of the room to the other, the rotation of the room changes the apparent path of that movement. On Earth, the Coriolis effect is large enough to influence weather systems and ocean currents, but too small to be felt by a human body in everyday movement. Inside a centrifuge spinning at the rates required to generate 1 g at short radii, the Coriolis effect is large enough to be felt with every head turn. The sensation is not subtle. Test subjects in rotating room experiments at NASA in the 1960s and 1970s described it consistently as a sense of the room tilting or swinging when the head moved, independent of any actual motion of the room. The faster the rotation and the shorter the radius, the more pronounced the effect. At the rates required to generate 1 g at radii achievable within current launch constraints, the effect is prominent enough that trained test subjects required days of adaptation before they could move normally, and some subjects did not adapt at all. The 1968 NASA centrifuge rotation studies on Earth tested trained subjects at the rotation rates that compact artificial gravity designs require. The findings were consistent across subjects. Vestibular conflict was severe at rotation rates above about 4 revolutions per minute, meaning that a structure generating 1 g through rotation needed a radius of at least 50 meters to keep the rotation rate at or below that threshold. And that 50 meters was a floor, not a design target. The study's conclusions were incorporated directly into the design principle that artificial gravity habitats must be large to be habitable. The principle was documented. The principle was not tested on a planetary surface because no rotating habitat has ever been built on a planetary surface. Every number from the 1968 studies came from Earth-based centrifuge tests, where the maintenance supply chain was a truck ride away, and where the experiment ended and the subjects went home. At 50 meters radius, spinning at 4 revolutions per minute, the structure still produces a Coriolis effect. It is just below the threshold at which most subjects experience acute disorientation. Below the threshold means habitable, not comfortable. It means that most people, most of the time, can move through the space without experiencing the room tilt sensation that shorter radii produce. It does not mean the vestibular system has adapted to the rotation. It means the rotation is slow enough that the conflict between the centrifuge's artificial gravity and the inner ear's rotation signal stays below the level at which the brain actively rejects the mismatch. The brain does not adapt out of the conflict. This is the biological fact that distinguishes Coriolis from motion sickness, and it is the reason pharmacological suppression appears in every long-term artificial gravity discussion as a management tool. Motion sickness typically resolves over days to weeks as the brain recalibrates its expectation of what normal movement feels like. Coriolis conflict in a centrifuge does not resolve in the same way because the conflict is not a calibration error. It is a geometric fact of the rotating environment that is present in every single head movement, regenerated fresh every time the person moves, regardless of how long they have been living in the rotation. The brain cannot learn to expect the Coriolis deflection and cancel it out because the deflection direction depends on which direction the head is moving, how fast, and at what position in the rotation cycle. The signal is different every time. There is nothing for the brain to learn. You are the mission medical officer. Month 8 on the surface. The 2 crew members with the worst documented Coriolis sensitivity, identified in pre-mission screening, rated as borderline acceptable for the mission rotation rate, are now averaging 2 episodes per day of significant vestibular disturbance during normal work activities, not during centrifuge entry or exit, which are the transitions most protocols flag as high risk. During routine tasks, reaching for a tool, turning to address a colleague, bending to examine equipment near the floor. The vestibular suppressant in the medical inventory was dosed for 60 days of acute management during the initial adaptation period. The crew is on day 240. The suppressant is gone. The bearing inspection scheduled for this week has been postponed twice because the 2 crew members trained for the EVA component of the inspection are both currently grounded with vestibular symptoms. The inspection requires working at the centrifuge's external mounting points in Mars's 38% gravity, where a vestibular episode mid-task produces a fall with no certainty of recovery. The inspection has been rescheduled for next week. The bearings have been running for 37 days past their recommended inspection interval. The generational question is the one that the bearing inspection and the Coriolis management and the radius trade-off all sit below. Children are not ISS astronauts. They are not trained test subjects from a 1968 NASA study. They are organisms in development: bone, nerve, cardiovascular system, vestibular apparatus, all building their baseline calibration from the sensory environment they grow up in. A child born inside a rotating centrifuge on Mars grows up with a gravity vector that is not uniform in direction, not consistent in magnitude between head and feet, and contaminated by a Coriolis deflection in every movement. The vestibular system that develops in that environment develops around that environment. The skeletal loading that shapes bone density and joint geometry during childhood is the loading that centrifuge rotation provides, which differs from Earth loading in ways that grow more significant as the child grows taller and the gravity gradient across their body increases with height. No documented outcome exists. The data set is empty. The human body's developmental response to rotation-based artificial gravity in a partial gravity planetary environment has never been observed in any subject at any age, because no human being has lived in that environment. The colony that commits to the centrifuge as its gravity solution commits its children to being the first data points in a developmental study that was never designed, never approved, and cannot be ended once it begins. Rotation is not neutral. An environment defined by rotation shapes everything inside it: the fluids, the vestibular apparatus, the cardiovascular gradients, the skeleton of every child who grows up in it. And it does so continuously, whether or not the machine is performing as designed. The colonists who chose to live inside it to escape the biological cost of Mars's 38% gravity have not escaped the biology. They have exchanged one biological constraint they did not design for a different one that they built, powered, and will maintain until the day the bearings give out. NASA's Mars surface architecture studies, the most current being the Moon to Mars architecture published in 2023 and currently being refined for Artemis-era follow-on missions, treat artificial gravity as a research priority and a long-duration mission risk, not as a solved infrastructure item. The architecture does not include a baseline rotating habitat on the Mars surface. The bearing problem, the Coriolis characterization gap, and the developmental biology unknown are each listed as open research items requiring resolution before a permanent surface rotation habitat can be designed to a confidence level that justifies the mass and energy commitment. The studies are ongoing. The launch windows for the first human Mars mission are being calculated now. The question that the physics leaves open is not whether a centrifuge can be built on Mars. A structure can be built. The question is whether the structure that can be built, at the radius achievable with the materials and energy a crewed mission can deliver, produces a biological environment that is less damaging than the 38% Martian gravity it was built to replace. The number is not in the research literature. The number requires a test population living in the relevant conditions for the relevant duration. That population does not yet exist.